Alright everybody, welcome back. In this video we're going to talk about concepts from section 8.8 of AP Calculus, volumes with cross-sections, triangles, and semicircles. In the last section we introduced the basic idea of how to find volumes with cross-sections, where all we really need to do is find the area of the cross-section and then set up an integral in order to find the volume of the cross-sectional solid. The only real difference between the last section and this section, last section we used cross-sections that were squares and rectangles. In this section we're going to use cross-sections that are triangles or semicircles. And we're going to look in the first page here at developing the area formula for the most common of these. Now certainly you can, with triangular and cross-sectional areas, you can draw a picture every time and go through and utilize the things that you know about triangles or semicircles in order to develop these formulas every time you need them. Or if you can remember the common formulas for various, for the most common types of triangles and for the semicircle, that can save you a little bit of time. Alright, so on this page we're going to go through and develop the area formula for the most common types of triangles that you'll see in these problems and for the semicircle, based off the side length of the slice. In every single one of these diagrams there's a dimension labeled S, and that dimension labeled S represents the slice coming from the base of the solid. So, if we're talking about this solid being formed between two curves, whatever the distance is between those two curves, that represents S in these diagrams. So let's come up with the area formulas for these common contexts. So an equilateral triangle with side length S, in order to find the area of this triangle, we're going to find the area like we find the area of every triangle. 1/2 base times height is always the area of our triangle, but we need a base and we need the height. So I'm going to extend an altitude from our vertex up the top here down to the base of this triangle. And now there are some dimensions that I can get here. This is 1/2 times the length of the side. And when I cut an equilateral triangle like this, it makes it a 30, 60, 90 triangle, which means that this dimension here is √3/2 times the length of S. Okay, so when we go to find the area of this triangle, the area is equal to 1/2 times the base times the height. The base is just S, and the height is the length of this altitude, √3/2 times S. And so simplifying this, we get that the area of the equilateral triangle is always √3/4 times the side length squared. And so anytime we're trying to find a volume of a cross-sectional solid involving an equilateral triangle, we can just put a constant √3/4 out in front of the integral, and then have the side length squared as our integrand. Alright, next, an isosceles right triangle with the leg formed by the slice. So if this is isosceles, these two sides are congruent, which means that both of these sides are S. So again, going back to area equals 1/2 base times height, we've got area equals 1/2 times the base, which is S, times the height, which is S. And so the area in this situation is 1/2 S squared. So if we have an isosceles right triangle where the leg is in the base of the solid, this will be our formula that we're going to use for the area of a cross-section. Isosceles right triangle where the hypotenuse is in the base of the solid. Alright, so let's see. If I extend an altitude to this side here, what I've created is I've created 45, 45, 90 triangles here. This distance right here is 1/2 of S. And since this is a 45, 45, 90, that means that this dimension here is also 1/2 of S. And so the area of this triangle, area equals 1/2 times the base. The base is S, times the height. and height is 1/2 s. And so simplifying, there's my area formula when I've got a right triangle with a hypotenuse as the base, or a hypotenuse in the base of the solid. All right. And then a semicircle with a diameter formed by the slice. Okay, so if this is my diameter, that means that my radius is 1/2 s. And the area of a semicircle, the area of a circle is pi r squared. A semicircle is half of a circle. So the area of a semicircle is 1/2 pi r squared. And so since the radius of this semicircle is a half of the slice that comes out of the base of the solid, that means that I'm going to replace r here with 1/2 s, and simplifying all this out, we end up with the area being pi over 8 times the side length squared. And that's a formula for our area when we have a semicircle, semicircular slice. Okay? All right, let's put these into practice. Another thing you need to be aware of, again, I kind of casually mentioned this, along with all of these and the ones we looked at in the last lesson, we can find volumes using cross-sections for any shape with a well-defined area formula. I've seen some problems on the AP exam over the years where they say, hey, you know, the cross-sectional area of this is, and they'll just give you any old area formula, and then you need to use that as your integrand. Or I could really do any shape. It just gets a little bit more complicated. You know, I could make a solid where the base is a regular hexagon and the side length is one of the sides of the hexagon. It takes a little bit more work to figure out the volume formula, or the area formula, but I could do it. All right, example 1. A solid lies between planes perpendicular to the x-axis at x equals 0 and x equals 3. The cross-sections perpendicular to the x-axis are equilateral triangles with the length of a side defined by y equals x cubed over 4. What's the volume of the solid? So we've got y equals x cubed over 4, whatever that looks like, between x equals 0 and x equals 3. Quick rough sketch. So our solid looks like this. Our slice goes from the curve y equals x cubed over 4 to the axis here. So that's our side length. And so now we need to set up our area formula here. We're told that this is an equilateral triangle with the length of a side defined by this. So our solid actually is an equilateral triangle where the length of the side is that. And so the area formula for an equilateral triangle, it's square root of 3 over 4 times the length of a side squared. And so that's going to be what we do to calculate our volume for this solid. And so we're going to have square root of 3 over 4 times the integral from 0 to 3 of the quantity x cubed over 4 quantity squared with respect to x. And I can go ahead and, calculate this by hand, or I can use my graphing calculator. It's really up to me. I'm going to go ahead and just calculate a decimal value out here. So I've got square root of 3 over 4 times the integral of x to the 6th over 16 with respect to x from 0 to 3. And our volume here is 8.455 for this solid. Example 2. From the 2014 AP Calculus AB exam free response question number 2, this graph should look familiar. We've already used it to do something else. in an earlier lesson. Region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. Isosceles right triangle with a leg in R. Do you remember the formula for that? If not, flip back to your previous page. Isosceles triangle, right triangle with leg formed. So that's going to be 1/2 s squared. So this is going to be 1/2 s squared. We're talking about cross-sections perpendicular to the x-axis. Okay. So my side length here is going to be the upper curve, which is 4, minus the lower curve. So my side length is going to be this. If I simplify that, these 4's cancel out, and I end up with a side length of 2.3 x cubed, x cubed, minus x to the 4th as my side length. And therefore, my sample area is 1/2 times 2.3 x cubed minus x to the 4th, quantity squared. So I set up my integral, got 1/2 times the integral 2.3 x cubed minus x to the 4th, quantity squared, dx. I need my limits of integration. Starts over here at 0 and goes to this point here. If you don't remember, this point was 2.3 comma 4. You can find that by just graphing the curves and finding the intersection. And so there's my upper limit of integration. And now I can go ahead and just calculate out the value of this integral to find the volume. 1/2 times the integral of the quantity 2.3 x cubed minus x to the 4th, that whole quantity squared, with respect to x, from 0 to 2.3. And I get that the volume of the solid is 3.574, where 3.573 is also acceptable. All right, we're going to call it quits for today, or quits for this video. We'll be back in a second video on this section with some more examples. See you then. Have a great rest of your day, everybody. Bye-bye.